Welcome back. In this video, I'll do one example to show you how we can evaluate a line integral without parameterizing the curve by using the fundamental theorem. That is, essentially by anti-differentiating, or more specifically, finding a potential function. So the question here is asking us to evaluate the line integral of a vector field. This vector field is called G, and it's along some curve C. Get ready for this. The vector field G is not terrible. It's a little more complicated than the ones we've seen, but the curve C is off the wall. Right. There is a parameterization for this curve. We are not going to spend time even thinking about it. Remember what the FTC for line integrals can do for us. I'll write it a little differently than I did above. The line integral of our vector field along some curve C will be g of q minus g of p, where g is a potential function. Oops, that's not what I meant to say. G is a potential function for a vector field, capital G. And P and Q are the start and end points of the path C. So here we are. We want to evaluate this line integral, and to do it essentially without parameterizing the curve, we need to figure out what's this function G, that is, what's the potential function of our vector field, and then what are these points, P and Q. Well, the points are easy. Our vector field is starting, our curve, if we look at the arrows, start at 0, 1, which is P, and end at 4, 0, which is Q. So the work we have to do now is finding what is this function, little g. So, well, if little g exists, then we know that gx, the partial with respect to x, has to be the first component of our vector, and we know that gy has to be the second component of our vector. And there's no reason we have to start anti-differentiating with respect to x. I guess let's just have it. I don't know, just for the heck of it. Maybe let's start with respect to y first. We'll take an antiderivative with respect to y, which tells us that our function g should be of the form x y squared plus 3y plus some constant which could potentially depend on x. And now, if we take a partial of that with respect to x, we should get, well, a partial of g with respect to x. And that will be, looking at this and taking a partial with respect to x, y squared. 3y is constant as far as x is concerned, so that just disappears, plus c prime of x. But just like we saw before, g of x, because it's part of the gradient, is also equal to 2x plus y squared. So combining this, y squared plus c prime of x equals 2x plus y squared. We can cancel out our y squareds. C prime of x is equal to 2x. Anti-differentiate, and we say c of x is equal to x squared, possibly plus a constant. We'll call that d again. So once more, we said g looks like this, which involves this function that might depend on x, c of x. And then we found what c of x would be. So combining all that, use purple again. Our function g of xy, our potential, I don't mean to say this is a candidate. Remember, it's called a potential function. The function whose gradient is our vector field. This is xy squared plus 3y plus x squared plus some constant d. Just like we do with definite integrals in Calc 2, if we're actually plugging it in to subtract at the endpoints, we can put in any constant we'd like. So maybe let's just leave that to be 0. And then apply the fundamental theorem. We said what our endpoint was 4, 0, and our start point was 0, 1. So we just need to know what these values are. Let's see. If y is 0, then the first two terms disappear. We get just 4 squared, which is 16. And if x is 0, the first and the third term disappear, and the middle term is just 3. So our answer for this vector field, 13. Which was a lot of work with all this anti-differentiating, but we really had no chance of doing this using parameterization of C. So you can take a look in the book, and we'll do some more examples of this in class.